Hello, everyone. Today, we will continue discussing our topics in power transformer. So in the last session, we discussed together the uh, evaluation of the single-phase transformer. So we discussed the efficiency, and we discussed also the voltage regulation. And today, we will start in a bit advanced topic in transformer, which is three-phase transformer. So firstly, if we would like to figure out what type of transformers we are using in power plants, so we have transformer after the generation stage. This transformer is stepping up the volt from several kilovolts to up to hundreds of kilovolts, like 500 kilovolts. And then we have the transmission step. If you remember that, we discussed that in the earlier stages of this class. Let me show you here. Yeah, this is the chart that we discussed in the beginning of our classes. So as you can see here, guys, this is our network, for instance. So we have generation at 30 kilovolt. Then after generation, I need stepping up to start transmitting this power. So stepping up to 500 kilovolt, and then stepping down in many steps according to the required load. So it could be 44 kilovolt, 4.6 kilovolt, until having the domestic loads, which is 120 volt. So all of these types, guys, are three-phase transformer. These are not single-phase transformer, because we transfer the power, we generate the power in three-phase form, not single-phase form. However, for single-phase circuits, we use single-phase circuits with light loads. But if the load is heavy, so we have to transmit to three-phase. So experience, guys, by experience, you can say, like, if the load is more than 6 kilowatt, for instance, so we can transfer from single phase to three phase. For that, guys, most of high power devices are three-phase devices. So if we go now to check the three-phase transformer, so three-phase transformer, guys, is nothing but three single-phase transformer or constructing a transformer in a bank. So making the three-phase transformer can be by using three single-phase transformers or by forming three windings in one core, and this is going to be three-phase core transformer. So let's follow up the definitions we have right here. Three-phase transformer bank. Let's start with the three-phase transformer bank. So three-phase system is used to generate and transmit bulk electrical energy, as we described together. So bulk electrical energy are all of the time in the form of three-phase. Three-phase transformer. Sorry. Three-phase transformer are required to step up or step down the voltages in the various stages of power transmission, as we could see in the slides of the different voltage levels. Three-phase transformer can be built in one of two ways. So what are the two ways? The first way is by suitably connecting a bank of three single-phase transformers. So this is the first way, guys. So we can grab three single-phase transformers and connect these transformers together in order to perform or construct a three-phase transformer. So this is the first way. And this is called the bank of three-phase transformer or three-phase transformer bank. Or by constructing three-phase transformer on a common magnetic structure. So we can create a magnetic structure for three-phase and construct the windings on this core, and in this case, this would be a three-phase transformer, not a three-phase transformer bank. So this is the way how can we create a transformer. So we have two ways. First way is by constructing three single-phase transformers, and we call it three-phase transformer bank, or creating a three-phase transformer on a single core, and this is called three-phase transformer. Later on, I will show you guys some cores, how can we do that, and how can we make a windings in what's the meaning of former and what's the meaning of window space. So all of that will be described in our classes. A set of three similar single-phase transformers may be connected to form three-phase transformer. So it has to be identical. If we are going to construct three-phase transformer using three single-phase transformers, these transformers have to be identical. How can we connect the three single-phase transformers together? You know that the well-known three-phase connections are Y connection or delta connection. So the primary and secondary windings may be connected in either Y or delta connection. We have some other connections, guys, called zigzag connection. We have a recent connection used a lot in research, and now sometimes you can find it in industry, called open end. We have what's called open delta. This is well-known connection. So we have a lot of special connections. However, the two well-known connections are Y connection or delta connection. So we have now primary side and secondary side. So we may have Y delta transformer, which means primary is Y connected and secondary is delta connected. We may have delta Y, so primary is delta connected and secondary is Y connected. Or we may have delta delta and YY. So both primary and secondary are identical in terms of connection. Okay. However, for sure, primary and secondary are different in terms of cross-section area, different in terms of the number of turns, and so on. Okay. So here, guys, we understood that, again, we can create three single-phase transformer and make the connection, and we can create a single core three-phase transformer. Let's see together, guys, the first connection, which is Y delta. So as you can see here, guys, this is the first phase, has turns N1, and here is the corresponding phase, this is the corresponding phase, has turns N2. So we can say that turns ratio of the single phase transformer is N1 divided N2. So this is the single phase transformer turns ratio. Now, if we connect the first winding or the primary winding as Y connection, so as you can see, this is the beginning of the coil, this is the end of the coil. So the three ends of the coil are connected together to one terminal, which is the neutral point. And the starting points of the three phases are connected to the supply from this side. So this is Y connection. The coupled volt, you know for sure, guys, all of you are aware of the three-phase coupled volt. So if the coupled volt is V, in case of Y connection, so the phase volt is V coupling or V line to line divided √3. So this is here the effective phase volt on the transformer. For single phase transformer, you know, guys, this volt divide the secondary volt equals N1 divided N2. So if I would like to write down here, let me write down this with you. So I'm going to call the turns or the terminals names. So I'm going to say this is capital A, B, and C, and this is the neutral point. So we have now VAN equals VAB divided root 3. So this is the phase volt. And since this is 3 single phase transformers, so we have VAN divide VB. I'm going to say B only. Okay. And according to the connection, now we will see what is the second letter. So phase A divide phase B, this is equals to the turns ratio of the single phase, which is N1 divide N2. So I know also that, or you know also that, this is equals, sorry guys, instead of VB here, I'm sorry, I mean VA, little a, not VB, just a moment, sorry. So let me correct that. Sorry, the phase A in the primary is corresponding to the phase A of the secondary, okay, which is little a. So I'm going to call this point A. I can say this is A1 and this is A2 for the time being. So I'm going to say VA1, A2. So this is the primary, sorry, this is the secondary of the first phase of our transformer. I can say this is equals the opposite current turns ratio, which is I little a divide I capital A, because I little a is going to be the secondary current here, and I'm going to say this is I capital A, and this is here I little a. Okay, so this is the turns ratio that we know about the single phase transformer. What about the three phase turns ratio now? So from the primary side here, it's Y connection, and we said that this is V, which is a line-to-line volt, and V phase equals V divided root 3. And this is the turns ratio of the single phase transformer, and the second volt here is the volt V little a is going to be the same as V between terminal, let's say this is terminal A, this is terminal B, and this is terminal C. So I can say here VAB equals the same as the volt of this winding, which is nothing but VAN times N2 divide N1, which is V divide turns ratio. So I'm going to say turns ratio, I'm going to call this is equals letter A, which is the turns ratio. So this is now V divide A. So this is the magnitude of the volt across this phase here, which is the same as the line-to-line volt. And for the current, if this is the current IA equals I, so I'm going to call it I. So I'm expecting here the current of the phase is going to be A times I. A is the turns ratio. So in this case, guys, if you would like to get the turns ratio of the three phase, which is coupling volt 1 divide coupling volt 2, it's not going to be N1 divide N2 anymore. So this is very important to be figured out when you solve the numerical problems in three-phase transformer. So you can convert everything to a single phase and use the relation of the single phase. And after, make all the calculations on single phase, start relate to the three-phase connection and get the line values. So here, for instance, I knew that the current here is turns ratio A times I. And this is the phase current of the delta connection. So this means the line current is nothing but root 3 times phase current. So I'm expecting here the line current is going to be root 3 times turns ratio times the primary current. So this is the value of the current that we will see in the secondary side if the transformer connection is Y delta. So this is just to understand, guys, how to calculate the values. But the question, where can we find the Y delta transformer? So here it's written, guys, in the textbook. This connection is commonly used to step down a high volt to a lower volt. The neutral point to the high volt side can be grounded, which is desirable in most cases, mainly for protection. So it's desirable for protection to have ground connection to this neutral point here. So here he mentioned, guys, in the textbook that Y delta connection is used to step down. So you can find this in substations. So for the substations, for instance, from 15 kilovolt to 480 volt. So this could be a substation transformer. So for such level, guys, the connection is going to be Y delta. But sometimes we may find delta Y still in the same application for the substation. But this can happen if you need Y connection in the secondary side, if you have single phase loads. So you need to have single phase loads. So by experience, guys, we can say that 80% of transformers, of substation transformers, are delta Y. 80% of substation transformers are delta Y, because 80% of our substations are desired to supply domestic loads. So this is this number actually from a transformer company. So they say that they can sell like 80% of their product as delta Y connection for substations. So this is what we have in industry. But this doesn't mean that Y delta connection is not there. No, Y delta connection is still there and used for industry, because for the industry load for factories, we don't need to have single phase a lot. So we can have the we can have the delta connection, and after that, if we need to have Y connection for single phase load, so we can have a small transformer. Okay, so this is for the Y delta transformer connection. Another connection is delta Y. So we just said, yeah, it could be used also in substations. And as we mentioned, 80% of delta Y of substation can have delta Y transformer. So delta Y transformer, the primary is connected as delta, as you can see, and the secondary is connected as Y. And still, the secondary neutral wire can be used for protection and for distribution between the single phase loads. Okay, so this can be also exist in substation. So this is also for the medium volt to low volt conversion. Okay. In terms of the turns ratio, let's investigate this together. So if this is the V line to line, it's going to be the same across the phase. So if we assume that the line current is I, so the phase current is going to be I divided root 3, the current will be transferred by the turns ratio. So we expect the current here to be A times I divided root 3, which is the phase current here. So this is A times I divided root 3. And since the line current is the same as the phase current in the Y connection, so this is going to be the output current here. So the output current here is A times I divided root 3. So again, if we compare that to the single phase transformer, we have input current I. The output current is not A times I. Here it's A times I divided root 3. Why? Again, because the connection is different. For the volt, we said that we have a phase volt equals line-to-line volt, which is V. So the phase volt will be V divided turns ratio. This is the phase volt, and for Y connection, line-to-line volt equals phase volt times √3. So the line-to-line here is going to be √3 V divided A. So this is the delta Y connection transformer. For the delta-delta or Y-Y connection, you will find that turns ratio are going to be respected by the same way like single-phase transformer, which means if you have V in the primary, the secondary is going to be V divided A. It's like single-phase transformer now. So this is the in case of identical connection. Again, here for the current, this is I. So the phase current is I divided √3. So it would be transferred to the other side, the secondary side, by multiplying the turns ratio. So I divided √3, and then multiply times √3 in order to get the line current. So it would be A times I. So it's typically like the ratio of the single phase transformer. This is delta-delta connection. So delta-delta connection, guys, have the advantage that one transformer can be removed for repair. This is very important. But the question is, let me firstly make some numbers here to allow you imagining how we can remove a transformer. So I'm going to say this is winding A, which is primary of the first transformer of phase A, and this is the secondary of phase A. So this or these two windings are forming one single phase transformer. If I'm going to say this is B, so this is little b, this is C, this is little c. So we have now these three transformers. Guys, we have a lot of abnormal conditions in our network. You may have a fault due to any problem in your network. So we can remove one of the three-phase transformers. If it is three-phase transformer, not three-phase transformer bank, you cannot do that. You cannot do that. However, for the transformer bank, three single-phase transformers, you can do that without disconnecting your load, but with the condition of reducing our load. So if we do that, guys, you will find that you still can supply 58% of your load. If you remove one of the transformers, assuming that transformer A has a problem, so we can remove all of the transformer A from the circuit and keeping only the other two transformers, and it can work as open delta. So this is special connection called open delta or V connection. So this is one advantage of using transformer bank compared to three-phase transformer. What is the advantage again? The advantage is you can disconnect one of the transformer for repair or maintenance. However, for a three-phase transformer with a single core, you cannot do that. So this is one of the advantages of that connection. And again, this can be only happen in delta-delta connection. You cannot do that in delta Y or Y delta. Okay, guys. So this is for the delta-delta connection. It can be open delta transformer. The last connection is the Y-Y transformer. So you can find the Y-Y transformer as well. Most probably required if you need the ground neutral. Okay. So in this case, as you can see, we have still identical ratio between primary and secondary. So this is I times A, like the single phase transformer. Here, this is V divided A, like the single phase transformer. So we don't have changes between the turns ratio between single and three phase in case of Y-Y connection. What about, or what is special in this connection? So this connection is rarely used because of problems with the exciting current and induce voltage, in particular of nonlinear loads. So you don't have a lot of Y-Y connected transformer in our network. Okay, guys. So this is the last connection of the three-phase transformer. Okay. Now, guys, if you have Y delta transformer or delta Y transformer, you will have a phase shift between the first phase in the primary and secondary. Why? Because you know that if you have different connection, Y and delta, between primary and secondary, you know that there is a phase shift of 30 degrees between line and phase voltages. So this will make a phase shift between the primary and the secondary volts. And it would be multiple of 30 degrees. So we have something called group number. So the group number is starting from group number 1 to group number 11. So these group numbers are nothing but multiple of 30 degrees. So you can have a lot of phase shifts between primary and secondary. Okay, guys. According to what? According to the phase shift between the primary and secondary of the Y delta or delta Y transformer. Some of the three-phase transformer connection will result in a phase shift between the primary and secondary, line-to-line voltages. This will happen if you have different connection. For instance, consider the phase voltage for Y delta connection. So here, in this figure here, guys, we have Y delta connection. So the phasors VAN and VA are aligned. So this is VAN and VA for the secondary. Both are aligned. However, the line volt VAB of the primary leads the line volt VAB of the secondary by 30 degrees because the primary is Y connection and the secondary is delta connection. So if you would like to get the line volt from the primary winding, so you would get that VAB is leading VAN by 30 degrees. You know that VAB is nothing but VA minus VB. So this is VA, this is minus VB. The summation of these two vectors is nothing but our VAB. So VAB is leading VAN by 30 degrees. However, for the secondary winding, still VAB and VAN are in phase because this is delta connection. So the phase and line voltages are the same. So in this transformer, the primary is leading secondary volt by 30 degrees. This is for the coupling volt, guys, not for the phase. So the coupling volt or the line-to-line volt, the primary is leading secondary by 30 degrees. Also, it can be shown that delta Y connection also provide a 30 degree phase shift between line-to-line voltages, where delta and delta and Y connections have no phase shift in their line-to-line voltages. So again, guys, if you have different connection in primary and secondary, this would lead to a phase shift between primary and secondary. By the way, guys, sometimes this makes a lot of problems. Why? Because in our network, if you have like any kind of disconnection due to any maintenance, and when you return the connection back, you have to be sure that the cable that will be connected is going to be in phase with the supply. Otherwise, you will make a short circuit. For that, guys, there was one of the capstone projects, I believe 2 years ago, was related to how to make check for the phase shift between the connected cables or transmission lines. Okay, so this project was made, I do believe, 2 years ago in our school, and Dr. Hattaboglu and I think Dr. Davari were the advisors, and I help also sometimes in this project. So it was very interesting project, and they could make a device to detect the phase shift before of making connection. Okay, if the phase shift is 0, so we are good to connect the transmission lines. If the phase shift is not 0, which is going to be 30 or multiples, so we shouldn't make such a connection. So it was a very interesting device, has a lot of constraints in design because the galvanic isolation and working with medium volt, but your colleagues could do that perfectly, and it was very nice platform. So again, we can have now the 30-degree phase shift between primary and secondary if the connection of the primary and secondary of the transformers are different. Okay. This property of phase shift in Y delta or delta Y connection can be used advantageously in some applications. So what are the advantages of this phase shift? Actually, you will find something in what's called 12 pulse rectifier. For the 12 pulse rectifier, guys, we need to have a phase shift of 30 degrees. So this is one way we use it in power transmission. We use it between networks or in DC transmission line. And we need this type of rectifier, and this type of rectifier needs the transformer to have delta Y connection in order to provide the phase shift of 30 degrees. So you cannot do such transformer without such a connection. So this is one of the advantages that we need it in the applications. Okay, guys. So in power electronics class, you will learn more about rectifiers, and you may also learn about the 12 pulse rectifiers used in power transmission. Now, after figuring out the different types of connections of transformers, we need to know how to make an equivalent circuit for our transformer. So, firstly, in terms of equivalent circuit, guys, it's going to be the same like single phase. So a single phase equivalent circuit can be equivalently obtained if all sources, transformers windings, and loads impedances are considered to be Y connected. So if you assume that you have Y connection, you can easily say single phase circuit is nothing but one of the phases, and start solving your question as a single phase. The Y load can be obtained by delta load by the well-known Y delta transformation. So if you would like to solve the problem of Y delta, you have to convert the delta into Y. So if I have Y delta transformer, as you can see here, I can simply convert the delta connected load to a Y connected load, and then convert the equation to a single phase transformer. Okay, so this is one way that we can use in the equivalent circuit. How can we convert the delta connection to Y? Actually, all of the time we will use balanced loads. So for the balanced load, guys, you know that Z or impedance of Y or equivalent Y equals Z delta divide root 3, divide 3. So Z Y equivalent equals Z delta divide 3. So this is the relation if you would like to convert Z load from delta connection to Y connection. So if you convert that, this is our transformer here. Here we have N1 turns ratio. Here, sorry, N1 primary winding. We have N2 secondary winding. You know that if we have current I here, the current here is going to be AI. So here is going to be root 3 times AI. So physically, the current didn't change. So the current here would be the equivalent to the current here. The current here is the same as the current here because we didn't change anything. Regarding the volt, so you know that the volt here, if this is V line, so this is going to be V divided root 3 here between line and the neutral. So the transformed volt on the Y connection is going to be V divided root 3. And here, so the phase volt here is V divided root 3. So the phase volt here is going to be V divided root 3 times A. Okay, guys. So this is the phase volt right here of the line-to-line connection. If you would like to convert this delta into Y connection, so the equivalent Y is going to be the magnitude of the phase volt here divided root 3. So V divided root 3 divide root 3 again, so it would be V divided 3. So in this case, if this is V divided root 3, this would be V divided 3A. So this is the Y, and here by the end, the line to line is going to be the same as the line to line here. So in order to avoid this confusion, guys, I urge all of you to convert the circuit into single phase, solve the question as single phase, and then convert by the end to 3 phase. So now, if you would like to compare the turns ratio of this transformer in order to be solved as a single phase, you will find that this volt divided that volt represents the turns ratio. So V divided root 3 divides V divided 3A would provide the value of A divided root 3. So if you divide again, the primary volt is V divided root 3. The secondary volt is V divided 3A. So the equivalent here is going to be now 3 divided root 3 times A, which is A divided root 3. So this is now the turns ratio. For that, the equivalent single phase transformer turns ratio is going to be N divided or N1 to N2 divided root 3. Okay, guys. So this is the equivalent single line diagram of this 3-phase transformer. I think this is repeated. Okay. Now let's solve this example, guys, to see how can we solve the 3-phase transformer problem. And we will end up with this solved example today. 3 single phase 50 kVA. So 50 kVA is nothing but the S rated of a single phase, because he mentioned here 3 single phase 50 kVA. So we have 3 transformers, every one is 50 kVA. So I can say now the overall power is going to be 150 kVA. And every single phase transformer is 2300 volt to 230 volt. So this is the volt of one single transformer. So these 3 transformers, guys, are connected to form a 3-phase 4230 volt. For sure, guys, you know, in 3-phase, all of the time we refer to the line-to-line volt. So the 4000 here represents the V line of the primary side, and the 230 represent the V line of the secondary side. Now, I'd like to know what should be the connection, guys. So this is V line. Let's compare this to the single phase volt. As you can see here, do we have a similar number? No, it's not similar. If it is not similar, so this means this volt here represents the line to line of the phase volt, which is 2300. So 100% this is going to be Y connection. Let me repeat this point again. We need to form a three-phase transformer of primary volt equals 4000 volts. From three transformers, the phase volt is 2300. So in order to do that, you have to connect the primary as Y connection, which is going to make line-to-line volt equals √3 times phase volt. So √3 times 2300 is going to be 4000. So we understood that we have to connect the primary winding as Y connection. Now, for the secondary winding, the volt here is 230, and here is 230 as well, which means now the coupling volt, the line-to-line volt, is similar to the single phase volt. What is the connection that we have? V line equals V phase? Yes, right. So this should be now delta connection. So the transformer or the three-phase transformer has to be Y delta transformer in order to provide the volt 4000 for primary and 230 for the secondary winding. Then the equivalent impedance of each transformer referred to low voltage side is this value. So low voltage side, as you can see here, guys, low voltage side is the secondary side. So this is, I can say this is Z equivalent 2 because it's referred to the secondary side. Or if you like to make subscription low or high, so it would be Z equivalent low. So either are fine. So we can call it Z equivalent 2 or Z equivalent low. The three-phase transformer supplies three-phase 120 kVA, 230 volt, 0.85 lagging power factor loads. So this is our load. The load is 120 kVA. We just mentioned, guys, that the three transformers, every transformer rated is 50K, 50 kilovolt ampere. So this means our load is not going to absorb the rated power from the three-phase transformer because this three-phase connection now can provide power up to 150 kVA. But the load requires only now 120 kVA. So this means it's not rated. The load volt is 230. For sure, it's the same as the secondary volt of our transformer. And the power factor is given 0.85 lagging load. What we need to calculate here? Firstly, draw schematic diagram showing the transformer connection. For sure, guys, we figured out the transformer connection firstly from the voltages of our transformers. So from the three-phase connection here, or from the three-phase voltage needed of this transformer, we figured out that this transformer has to be Y delta connection. So simply we can draw now the Y connection to the primary side, delta connection to the secondary side, and then this is our load. So this is the solution of part A. Here, guys, the textbook describes the high voltage winding are to be connected in Y, which is the primary one, so that the primary can be connected to the 4000 volt supply. And the low voltage winding is connected in delta to form 230 volt system for our load. So this is our connection here. Part B, determine the transformer winding currents. Winding currents means phase current. So we have current right here and current here. We need to get the primary and secondary currents of our transformers. How can we do that? Let's start firstly doing our load calculations. You know that we supply a load of S equals 120 kVA. And the volt of the load, V of load, equals 230 volts. And it's connected as delta connection. So simply you can say for delta connected load, or general relation of power is S equals root 3 V line, I line, and you have S 3 phase, you have V line equals 230. So simply we can get the I line. So we can say now I line, which is I secondary side, equals 120 kilovolt ampere, so 120 thousandths, divide root 3 times 230 volts. So this is the line to line, or the line current of the secondary side. And remember that secondary side is delta connection. So if you would like to get the phase current of your secondary side, it would be I line divide root 3 because it's delta connection. So we can say now I 2, which is the secondary side current, equals I S, which is line, divide root 3 because this is delta connection. So 301.24 divide root 3 is 173.92, and this is the phase current. This is the phase current of our delta connection. Now we would like to get the phase current of the primary winding. We are now using single phase transformer because we get the phase value. We got the phase value, so we can use the single phase turns ratio. So I can say that V or I2 divide I1 equals N1 divide N2. This is the turns ratio of our transformer. This is the relation between current and volt. This is equals our turns ratio, which is A. And A is given from the single phase transformer, which is 2300 divide 230. This means it's equals to 10. So we can say now I2, we already got it, which is the secondary side current. So we can say I1 equals I2 divide A. So I2 is 173 divide A, so it would be 17.39 amperes. So this is the phase current of the primary winding. Remember that our connection is Y delta, and this is the primary winding current, the phase current. For Y connection, you know that the phase current equals the line current. So this is going to be now representing the ideal transformer secondary current. So, sorry, the ideal transformer primary current. So this would be now the value of the phase and line also of the primary winding. Part C, determine the primary voltage line to line. So we need to get the line to line volt of the primary side. If we draw the equivalent circuit of a single phase transformer, so this is the equivalent impedance, neglecting the branch of magnetization. So if this is V1, this is V2 prime, and this is the Z equivalent, refers to primary side for instance. So we can say, or if you would like to get it from the other side, because the impedance here is referred to the low voltage side, so we can say V2 prime, sorry, V1 prime, and this is V2 without prime. So we can say, let me correct that here. So instead of Z equivalent 1, this is now Z equivalent 2. And we have already Z equivalent 2 is given right here. So we can use now the secondary current, which is I2, and calculate the value of V1 prime, and then use the turns ratio to get the volt, which is a single phase. After that, find the line to line of the Y connection. So we can say here, So here, guys, he did prefer to transfer the impedance to primary, so it's going to be the same. So you have all options. You can use this solution or the other solution. So here in the textbook, he transferred the impedance to the primary side. How can we transfer the impedance to the primary side? Just multiply times the ratio square. So this is the impedance. We will multiply times 10 square. So this is now the equivalent impedance referred to primary side. So now we can say our primary volt equals V2 prime, which is nothing but the 2300 volt, and all of the time is going to be reference, as we mentioned, at angle 0. This is the value of I1 that we obtained, and the angle of I1 can be obtained from the power factor. So the power factor is given 0.85, so it's lagging power factor, so the angle is going to be minus, and cosine inverse 0.85 times our impedance. So from here, we can get the value of the primary volt, but take care, this is the equivalent single phase, which means this is the phase of the Y connection. You need to get the line of the Y connection, so you have to multiply this times √3. So this would be now the primary volt. Next class, guys, we can continue this example and continue discussing more topics and evaluation for three-phase transformer. Thank you so much and see you next class.